Any questions about the quiz before we get going on the next unit? Yes. So the quiz is very similar to the practice quiz. You've got 3 questions with a few sub-items, very kind of same format. Thumbs up is good. Say again? Same link? Oh, same length, yeah. Different link, same length. Yes, not same length. Similar length, yeah, it should roughly, does that seem like something you can do in the time you have? Well, yeah. It's good. Okay. Other questions about the quiz? At home, let's see, chat. Can I handwrite it using digital software like Stylus Setup? For sure. Yeah. Don't get into typesetting your quiz solution, because that's, you know, that's my suggestion. But sure, you can use a stylus. Caret, I don't know what that means, but that. Okay. Other questions about the quiz? Yes. Yeah. So we really enjoyed your voice recordings. We got like full monologues, you know, long things, you know. I was born in 1991. No, you were born in 2000s, but late 90s maybe. So quick one. I did the quiz. I hope you can say this. I did not plagiarize. If that's the case, that should be the case. Yeah, so it's just for that. Other questions about the quiz? So then you convert it to a digital thing and submit. Yeah, so the quiz, as you saw from the practice quiz, the solution will be a page or 2, right? Take photos, upload them to a Word document or something like that, and submit your quiz, your name on there, etc. So this is a quiz you're taking home, scanning and submitting. You're sitting at home or in a Starbucks or wherever, and you're getting the link at that time and you're doing the quiz. You don't speak with anybody during the quiz, and you follow all the other instructions. You can use these course materials on the web during the quiz, but nothing else. You don't run Julia during the quiz. Questions about the quiz? Technical, more? Okay, let's get going. So, all right, so what we're doing now is we're doing unit 4. Oh, wait, just quickly. I don't know what that means, but that's nice. Okay, so you can ask me questions in the just ad hoc. Do we need to submit the voice recording at the end time within the quiz? Yes. So the time of the quiz is, let's just see this very quickly here. So if you go to the site, you go to the quiz, you go to the practice quiz, you'll have here a link tomorrow for the real quiz, okay? Just in that time, all right? That has worked before. Read all these because it'll be the same text verbatim in the actual quiz. And the quiz is, you know, supposedly 50 minutes and 10 minutes reading and 20 minutes, 20 more minutes allocated to formatting solutions. Okay, so 80 minutes in total. If I got it correct? Yes, right? You can do anything you want in those 80 minutes, okay? But, you know, the quiz should roughly take 10 minutes and 10 minutes reading, etc. You know, like that. You read the quiz, don't, as in any UQ exam, read those first 10 minutes, ask questions on the private chat. You know, I don't understand what this symbol means. I don't understand what you're asking there, etc. That's not clear. At the end of those 10 minutes, I will broadcast the solution, well, the answer to those queries to everybody, okay? Somebody doesn't know what the arrow is, I'll say, look at the notes, okay? Or something like that. Or what do you mean explain? I'll say, that's what I mean by explain. Okay, that's the time to kind of ask about things like that. That's a standard. One more question. So the voice recording is just as confirming this our own work and we did not cheat. Yeah, so we developed this voice recording method back at the start of COVID. I think it's a pretty good thing because my assumption is that lying over voice is harder than lying in handwriting. Yes, so that's what it is. Yes. Not really. I mean, it's just like, you know, you can share a very quick experience. Sometimes it's, I mean, when we marking, you know, you say this quiz was completely unreasonable. You know, you could say that. Feel free, you know, you could. say anything you want. So that happens. So I've done a lot of these quizzes in master's courses, and you get an indication. It was easy for me, hard for me, but it's not the important thing. It's really it's a signature of that work is my own, and I followed the instructions. Okay, assuming you can say that. Okay. No more. All right. Okay. This is okay. So now we are here, and you get to be with me and Paul Verbeek. Paul, he hasn't come. He promised he will come. He must come next week because he will teach us the polynomial bits. But what we're going to do with me is a bit more in Unit 4 and a bit more of Julia Essentials. And this is kind of an iterative process. I mean, you dove very quickly into Julia. Just turn it down in the class just a bit. And we're going to see a few things in a bit more depth now. And then you'll see it more with Andy that will join in the last couple of weeks. So there'll be some final things that we'll see. But let's get with it. So if you go to Unit 4, so this is not for the quiz per se. Here's Paul. We were just speaking about you. Got lost. Fair enough. Okay. So yeah, Paul will actually start speaking next week, but we only have this just less than an hour today. All right. So what we're doing in this Unit 4, we're catching up on a variety of things dealing with Julia. Okay. And the highlight is really going to be your own user-defined structs. Okay. Your own user-defined types. But also types in general, multiple dispatch. But we'll just touch a variety of things and see how it goes. Now, I know that Andy did it in, like the REPL. I'll use probably iJulia more. So just because I like iJulia for this type of teaching. So I'll create this new thing, and this will be uploaded to GitHub. This is just scrap notes, okay? So the same type of calculation that were on the REPL. This thing will be during lecture of week 6. Okay, we'll see how it goes. All right, so, okay, we've seen a function, right? This is a one-line function. And nothing special about this function. I mean, this is just like defining the function as one-line function, but let's see a few more things with functions. So here we define a function f of x is simply squares, and it's a function with one method. Okay, and we'll get to understand today or next week what methods really are. We already are in this example, but we'll see it a bit more. Here we're defining a function. Why do we have int here twice? What's the first int and what's the second int? Right, exactly. The return type is an int, that's this thing, and the input of x is an int, right? But you guys have dove into Julia so quickly, you actually know a whole lot. Okay, just like said in the chat as well. So this function does the same thing, okay? But now there are two methods. So if you would run this, you'd see there are two methods because there's a method that works kind of with anything, okay? And this might fail because I might put in something that doesn't know how to square it. It will actually work with a string because you can square a string. It's like a string times itself. It concatenates with others, but maybe there are types that is not so squaring. This is just for inting. Now, this is a generic function. You've seen this from the first lecture, but you're now going to see them a bit more. Okay, and you'll fully deal with generic types when you meet Andy in a couple of weeks, but let's start to do it anyway. So here T is not any specific type, it's like a placeholder. I could have had an R or a Paul or a Johnny or whatever, okay? And T here is anything that is a number, is a subtype of number, okay? So this one is defined for ints, this one is defined for anything that is a number, okay? So that's the third method, okay? And this fourth one is just resyntaxing the third one, but you could have done this long form for anything, right? And as you know, the return function is, the return keyword is optional. It's a bit more verbose, but it's optional, okay? So if you do this, you have the function running on defined with 3 methods, Okay, Julia's multiple dispatch is all about when you have a function, that's that function name, the system in runtime decides which method to use. Okay, which method best suits it. Is it going to be, so say, if I run the function on a float, which method is going to be used? The first one, the second one, or the third one on a float 64? The third one, okay? It doesn't meet, it meets the criteria of the first one, but the third one, it meets it better. It's more specific, okay? It doesn't meet the criteria of the second one, okay? And if I run the function on a string, hold on one second. If I run it on a string, it'll be the first one. Yeah. Yeah. Okay, so we'll soon get, you actually cannot have a real object of number because number is an abstract type. So when we get to the type hierarchy soon, and soon I might be by next week, but we'll see how we do today. Okay, so some types are abstract and some are not. Mm-hmm. I think it would be the second one. So if you would run it on a bool, okay, so if you would run it on a bool, then it would be the second one. So, okay, so let's actually just do this quickly. Okay, we won't do it. I know that it's always tempting for the lecturer to do it on all of them, right? So to kind of this, but let's see. And here's a second one, and here is the third one. The fourth one, let's ignore because the fourth one is just different syntactic sugar for that. Okay, so the methods of F are of course this, and let's do which F of hello. I put a space, okay? Yeah, one sec. Right? So it's telling us it's hello and in11, so that's this one. Yeah. Right. When you have those three lines, it's not redefining F each time. It's like having different ways to do it. 100%. Yeah, if I would do this one, if I would do this and just decide that I prefer the syntax function this, where this is a subtype of number, return x2 and end, now I am redefining this third method, okay? So because it's the same signature. But indeed, with multiple dispatch, yeah, Julia keeps multiple methods for the same function, okay? And there's something in the chat. Does Julia know what is a number, or we have to define what is a number? Yeah, Julia knows what is a number. In the type hierarchy, there's a built-in type number. We'll get to type hierarchy. Okay. Yeah. So if we ran it, which on F this, it's the first one. But if we did which F of pi, or let's do 2.3, for example, it's going to be this third one, right? And in this case, it's an in6. It's not an in3 because this function was now redefined. But if we did at which F of true, so it's actually, well, okay, so here I'm a bit surprised. So true is a subtype. So the type of true is a bool, which is an integer. So if I do the super types of, sorry, the super type of the bool, it's an integer. Okay, but Julia actually here, this is a subtlety I'm not aware of. So it, it has F with an int, specifically with an int, but then I guess that makes sense. And it has F with anything that's a number. So when it has both of these things, it chooses the one, int will be just specifically for int. So if I do at which F of 24, it's running the one with an int. Okay. All right. So, but the key message, the details are not super important, but the point is we have functions and methods, okay? In object-oriented language, the word languages, the word method means something else. You have a class, which is a type, okay? And if you haven't done object-oriented languages, you haven't done Python or Java or C++ or Swift or anything, that's fine, okay? But just so you know, the word method means something else. A method is a function of a class. In Julia, a method is a specific signature, a specific implementation of the function, a specific type, form the function can work on. Okay, yep, so that's what you see when you run methods of, here, we did this. We ran the methods of f, and it has 3 methods. Yeah, go ahead. 100%. 100%. Right. Yeah. Now, sometimes this doesn't make sense, right? So sometimes you'd want actually the actual behavior to be the same, right? So the function that squares should be the same, but maybe squaring an int should be implemented in a different way than squaring a complex. But actually, in the project that Paul and I are now preparing for you, okay, you're going to have functions that work on integers and work on polynomials, okay? So you're going to do division, you're going to do Euclid's algorithm, which you probably know on integers, you're going to do it on polynomials, mod p, okay? And it's going to have different behaviors, even though it's the same type of thing. Now, RAND, for example, if you do methods of RAND, at the moment, you've seen this before, but this is just a recap, okay? And we're taking that step kind of a bit slower to just touch things again, because you really dove into Julia beautifully. I hope you feel so also, I'm not sure. Let me just assume you do. So if you look at the RAND function, RAND has many methods just with me not including anything else, because yeah, you can do a RAND of different types of different, you can put abstract random numbers there, you can do different things. And if I'll now use a built-in package using distributions, for example, no. Okay, and now look, there were before 70 methods for RAND. Let's now do methods of RAND. This package has added more methods for RAND. There's now 169 methods for RAND. Okay, I can do methods of the function plus, and there are 271 methods for the function plus. It might be a bit less if I was not with distributions, because maybe the package distribution, let me restart the kernel and do that. Let's do it methods of plus. Maybe the package distributions does not have, maybe it added a few methods for plus. In your project 1 that you'll only deal with after the end of this weekend. So again, after the quiz tomorrow, take a bit of a break. That's a suggestion. Yeah, so in project 1, there'll be methods for plus as well, for adding polynomials, okay, etc. You see, so methods plus without distribution was 190 methods, but if I now add distributions, not add, but incorporate the functions and types of distributions in namespace, and I do methods of plus, and we get to this 271. So distributions had some, you can overload the plus. Okay, in Python, this would be called, I understand, magic methods. In C++, it's called operator overloading, so you can do plus between 2 things. Okay, so now that we're dealing with functions, let's just, if you go to the Julia documentation of functions, what we have here is just a few things of making a bit of ground of things that you haven't seen per se in units 1, 2, and 3. So for example, return nothing. So this all the time links to the Julia documentation. So return nothing is just, you can have a function that returns nothing. Okay, so not every function needs a return type. Okay, maybe it does something to the system. For example, printing hello class would do something to std out to the system. Does anybody know what this is called in C, for example, or C++? A function that returns nothing, the word for nothing there. No, it's different generation. So it's void for void. Okay, we've got somebody in, thank you. Okay. Good. I mean, just a word. Okay, so returning nothing. So nothing is a Julia variable. If you do nothing, yeah, nothing is nothing. Okay, we can get philosophical. This is philosophy math 2504. You can do the type of nothing. The type of, you might have done this with Paul actually. The type of nothing is capital nothing. Okay, it's nothing. Okay. Argument destructing. This is a very minor feature, but just be aware of it. Be aware that it's a bit magical. So look, if I define the function f and I open round brackets x comma y, what is the type of this thing that I'm highlighting? Do you remember? Yeah. Tuple, right? So in Julia, you got arrays, kind of the main thing, but you've got tuples. Tuples are immutable. You see the thing. So this is like the function on a tuple. So you wouldn't immediately expect that you can give like x comma y in a tuple and tell the function how to reach x and y. But that's a little minor feature. You can read about it on the docs. It's called argument destructing, not much more than what we're showing. But all it means is that for now, for example, if I do a function make pair, which creates some random tuple, and if I do f of make pair, well, in this case, the pair actually, we were lucky enough, and the random number, so sum of their two values was 5. Okay, that's all. Just a very minor feature. Let's get now to something more serious. Functions with a variable number of arguments. Okay. So this you've already seen before, this ... Does anybody know what it's called? Do you remember? Splat. I heard a splat. Yeah, splat. Okay. So you've seen the splat operator in this context. For example, look, if I do myf, if I do myf and it works on x, y, z, and what it does is x plus y plus z. Very good function. Okay. So I can do myf and I could do a data is, let's say 1, 2, 3. Okay, that's my data. I can do I can't do myf on data. Okay, that's not going to work. All right, because it says I don't have a method for myf that takes a vector of int64. So that's a type of data, but I can do myf on data ... And what this asks Julia is to take the arguments of this collection, and this collection can be an array, can be a set, can be anything that's a collection. Okay, it can be a tuple, and pass it as arguments one by one. And yeah, 1 plus 2 plus 3 is 6. Okay, so that's a splat operator. Now, the same operator can also be used for creating a function. This is now in the function definition that gets a variable number of arguments. Okay, so sometimes when you create the function, you don't know how many arguments it's going to get. Here's, for example, a system function that does this is min. Min is the minimum. Okay. It's not the minimum, it's different. Yeah, min is, let me just write here, different from minimum. Okay, minimum works on an array and min works on x, y, ... Okay, so you can do min of 2, that's just 2. You can do min of 2, 3, that's still going to be 2. You can do min of 2, 3 and -1. Of course, that's going to be -1. And there aren't a zillion versions of this function min, so the language has to support for that. And the way the language supports for that is in the function signature, it says it'll use these ... similar to the splat operator. Okay. So, for example, I can say my min is minimum. My min of data is minimum is, no, that's what I want to say, is min of data ... Okay, so the reason I want to show you this is, look, I cannot do, this is data. I cannot do min of data. This is a system min. System min doesn't work on an array. Use minimum. Okay, that's a system min. Min doesn't work on an array. But here I've created my min, and this is just for demonstration purposes, which will apply min on the data passed as argument. So let's look at that. So my min of data, and it was 1. Okay, so what it did, it passed those arguments to the function. Now, if you want to, let's just write this a bit more. By the way, you can define functions like this. There's no real reason to. The only reason is if you're kind of writing quickly. Well, the only reason I kind of know of is if you're writing quickly and you then don't want to write the word function here. So you turn it from one line to multiple lines, okay? So I can do at show length of data. Okay, so this is just some for debug. And so if I do my min of data, the length of the data was 3. So it passes in the data, and then I can go on the arguments one by one. So in this specific example, and this says polynomial, but don't confuse this with the algebraic polynomial or polynomials with integer coefficients, etc. This is a polynomial that's going to be solved using a numerical method coming from the roots package. Okay, so let's analyze this code from start to finish. All right. So the function polynomial generator here, you're going to give it an array A, and it will return this thing. What is this object that it's returning? What is it? It's a function, right? So this Some people would call this a design pattern or a factory of something like that, but basically you're creating a function that returns a function. You're going to have these in your project as well. Okay, so the polynomial generator, excuse the fact that I'm not using here the naming convention of Julia. So I used to program more in C, and we'd used to use this, and it's called camel case. So when you have kind of the first capital thing, but with Julia, we like underscores. Okay, so polynomial generator, what it's doing is it's reading the length of the array. Now this is going to be the degree. The degree is going to be the length minus 1, right? Because a polynomial with, say, a first degree polynomial, an affine function has 2 coefficients, okay? And a quadratic has 3 coefficients, so it's length minus 1. And the way it's creating this function is it's just doing an evaluation of the coefficient times the power, okay? That's what it's doing. Of course, we could have improved this. We could have written it in as a one-liner. So let's run it first and then improve it as it runs. Okay, so we could just say poly of x. Could have done multiple improvements, I believe, equals this, and we could have just even return this. I mean, this improvement is not necessarily a good improvement, but it's just a syntactic improvement. That doesn't work. Return, oh no. Poly of x equals that and return it, sorry. Okay, so, and you could have also done without these if you'd like, and that's not a big deal. Okay. So the point is here is that polynomial generator, you know, you can put more coefficients to polynomial generator. And here we're using the built-in, well, not the built-in, but the function find zeros from the roots.jl package. Good package to know of. Again, this is not directly related to your project, which will deal with algebra as opposed to numerical root finding. Okay, so that's a roots.jl package. So this package, the function find zeros wants a function. Okay, so you can't just give it the coefficients of a polynomial, you need this other function that will create it. Questions about that? All right, this is stuff. Okay, good, so we know how we can do that. Optional arguments. So like many languages, in Julia, you can give optional arguments to function, and the way you would do this is, here is an example. So this is a density. Everybody, I assume, pretty much knows, yeah, you've all done one form of stat 1.301 plus some other things, you know, so the density of a normal distribution, here it is, e to the minus x minus mu squared divided by 2 sigma squared, the mean and standard deviation, sigma, all normalized by this thing. That's a square root function, right? So the density function of x, you would want to have the value of x, so the density function at x, and you'd want maybe these things. What are these? This is kind of, if you specify normal distribution, you don't say anything, you speak about the standard normal, right? So mu by default, you just give it a 0.0 and sigma 1.0. So then when you do my density of x, it just gets these default arguments. Okay, optional arguments, not much to it. There is a bit more to it in the sense that, and here we're comparing it to the inbuilt density, which you'd get from the distributions package. Okay, so this example here, just at its own, I'll just run this here, sorry, first above. I'll just run this and create density. The way Julia actually implements these optional arguments is if you do methods my density, it creates a version of x that just works on float 64. It creates a version that works on float 64 and the mean, so the standard deviation would take the default value 1, and it creates a version that works on float 64 where it specifies the mean and the standard deviation. That's all. Here, the way the distributions package work, you actually call this function. What do you find weird about the notation of this function that I've just highlighted, just in terms of the naming convention? Capital, right? So the reason this function, that's a naming convention, the reason it has a capital, this function is a constructor of the type normal. It's just a function, but it's a function that creates type normal. It's a naming convention in Julia to have type names, which we'll create soon, or packages to start with a capital letter. Okay, so if I do, for example, normal, that created for me a type, which is a normal distribution. Okay, this is kind of similar to the distributions in Mathematica. I don't know about Maple. The distribution.
They're very similar.
Yeah. So Paul is a Maple guy, as you know, or you'll know. Yeah, well, but he has a book with his dad on stats with Maple. Probability. Okay. Yeah, over the years, I've learned to call probability and stats the same thing. It's better for a variety of reasons. Okay, please stop me at any time. And look, jokes are always going to be cheesy or non-jokey at all. That's just the way it is in the computer science world. Or anyway. Okay, so you can also do something called keyword arguments. So by the way, if you go here to the docs, the point is these things link to the docs and the docs are readable. You know, optional arguments, you know, just a few examples. The docs here are readable. And soon you'll be going through all of Julia. The thing about this course is not necessarily Julia per se, but it's kind of a programming language kind of in its completeness, pretty much in its completeness, right? You'll go out to industry and you'll do the same with Python maybe, or with Scala, or with Rust. But you know, you kind of know what to expect in the programming language. And some of you have done it with others before. All right. Keyword arguments are a bit different. So here comes the semicolon. Again, Paul Bellet has alluded to this in the lectures, but he had to cover so much other material in the lectures. So now let's just see keyword arguments in a bit of a slower manner. So here I'm defining my density where I'm putting a semicolon between the mu and the sigma. And when you do this, these arguments become named. So I'll show you. So let's go here and define my density. And now if I do my density of, let's say, 2.5, just some point, and I can say sigma equals 5.3 and mu equals 2.5. Oh, let's not make the same thing, 2.3, whatever. The point here, look, first of all, you see the order mu and sigma. Here I've chosen to use a different order. So after the semicolon, you're naming the arguments. So the order you call them does not matter. Okay, so this thing is the same as my density if I would change the order. Okay. Now, you also don't need to actually have the semicolon. So some people use it in the function call, but you do need it in the function definition. So you could have put a comma, and Julia would know here that these are the, what are they called? The keyword arguments, okay? So that's it. And you could have actually done a few different things. You could have put a named tuple that has these arguments, and you could have even put a struct that has these arguments. So read more about it in docs of keyword arguments. Now, which function have you used a lot in your homework that uses a lot of keyword arguments? Not a function you wrote, but a function from a package. Plot. Plot has a gazillion keyword arguments, okay? So, and of course, you know, if you go to plots.jl, nice thing, by the end of this course, you guys are going to be much better at this, and certainly than me. I don't know about Paul and Andy because Paul Blett and Andy, because they work with it in industry all day, not all day, but a lot. So, but probably with the attributes, etc. So these attributes are all a bunch of keyword arguments you can use, and there are more of these. There's several types in the plots. So when somebody defined the plot function, they didn't write, and you could look at the source of plots.jl, okay? If that's your thing, all right? So they didn't define all these billions of options. What they did is they did that. So this is keyword arguments where you just write quargs, keyword args, ... splat, okay? I don't think this KeyWrx is a reserved word. It can be anything, but that's the common naming convention used for this word. Okay, so my very flexible function, plots is a very flexible function, okay, but there are many others. It gets here something which is anything. And here, if I will run it, And I've decided, see, Julia does not know to expect an A or a B or a C. Now, even one was a int and one was a string and one was a symbol. Okay, it gives me this thing which I can work with, the KeyWrx, right? So I can ask, for example, I can say at show KeyWrx dot B, and oh, it has no pair DB, sorry, maybe like that, sorry. I'm wrong. Pairs has no field B. So now I'm a bit worried. I'm not sure how to access this. So KeyWrx is this. It's an iterator. Okay, so let's do for arg in KeyWrx at show arg. And so I can iterate it and each one is a pair. Okay, so it requires a bit of querying. Okay, so you can, but when they do the plots function, they then iterate over all the arguments and see, do they change this from the default? Do they change this from the default, et cetera, et cetera. That's a KeyWrx. Yeah. Okay. All right. Some other tidbits. All right. The DoBlock syntax for function arguments. All right. So you've seen this type of thing. What's happening in this line? What's happening in this? So we get here 100 data points, and then we're calling this line that I'm highlighting. What is this thing that's happening? Right, we're doing the numbers divisible by 10. We're using the inbuilt function. What would you call this thing that I'm highlighting? An unnamed or an anonymous function? Hi, Amy. Hey, so an anonymous function. Okay, right. So we're defining an anonymous function that gets an X and returns this expression, which is a Boolean expression, right? Okay, so anonymous functions are good. But of course, what if I wanted a multi-line anonymous function? Of course, if you could say, if you want a multi-line anonymous function, just don't be lazy, just write a function. But if you write a function, you pollute the namespace, and you know, it's if you know that this function is only used in one place, it's kind of, to give it a name is painful. It's not so, you know, but you could do it like this. Okay, but look, this is a lot of JavaScript code, by the way, looks like this, like functions that span zillions of lines. All right, but you know, that's one way of doing it. Julia introduced this other syntax, which is the DoBlock, and it's the do keyword. This is not do like a do while loop. If you're looking for a do while loop, it doesn't exist in Julia, unfortunately. Okay. But the DoBlock is defining an anonymous function that gets as an argument X. Okay, you could have had multiple input arguments for this anonymous function. And it's then passed as the first argument to filter. Okay, it sounds a bit obscure, but the standard library often gets the first argument of functions like filter and count and other things as a function. Right? So if you look at if we look at the help of filter, filter applies the function f. Okay, so if, for example, I do filter on rand 10 points, do x return true, and of course this is a silly filter, but it's called this function that gets an input argument x and always returns true. Okay, or if I do return false, we're going to have an empty list. Okay, so that's this DoBlock syntax, which you see quite a lot, just so you know about it. Okay, so again, today is this intermediate lecture, a collection of kind of bits before we're getting to the beef. Questions about that? Yeah, so it's always the first argument. It's kind of nice to look at the, I suggest looking at the documentation for this, because you'll see there's even like an example where the open function, the system open function, okay, gets as a first argument something to do with a file. So you might open some file and you will run this thing that you tell it to do with it, okay, and then you close. This try and catch, we'll get to that in a second. This try finally end. Okay. All right. So next we have function composition and piping. This is even less important. You probably have seen this before. So this is just a syntax of saying, let's take this argument and pass it as an input argument to cosine, and pass that as an input argument to r cosine, and pass that into this anonymous function. Okay, so you would see this sometimes with 1 or 2 functions, not with 4, typically like that. It's used, for example, with, you might have seen it with CSV and data frames. It's kind of a common way of writing it. You do CSV read into a data frame. Okay, but that's just different syntax for applying a function. You even have this with a composition. Just if you want to feel a bit like a mathematician, if you're coding here, then this is a composition of cosine and r cosine. It's not a very good composition, is it? It does nothing really. Yeah.
Which way does it compose?
Like the standard way, so cosine of r cosine. So the standard kind of, yeah, I hope, yeah, it does. We can't tell with cosine and r cosine, but yes, no, that's. Oh no, we clash of cultures of. Okay, so then yeah, okay, so that's that. Now, of course, the dot syntax for vectorizing functions, you've seen this. This is critical, central to Julia, right? Cosine, what do you call this dot? What is this dot? The broadcasting operator, right? Okay, so broadcasting operator, you've seen, you might want to look at the broadcast function, okay? So if you dig into this a bit more, just look at the broadcast function, which does this thing, okay? So the dot operator is a way of doing broadcasting. There's a related function, not exactly the same, which is a map function. So you might want to look at that, okay? Map just maps a, like in many languages, a function onto a collection, okay? You might want to spend a bit of time to look at the documentation here, and it gives a bit of arguments what's happening about stuff that can happen, say, in Julia. I don't want to make this a Julia ad, but stuff that can happen in Julia, but not in NumPy. So the thing is, if you do cosine of sine, exponents, etc., and you do all this broadcasting, Julia can actually compile this into efficient code. So that you'll read this if you read this documentation, if you're a bit interested. But that's kind of extra from what we need. This macro you'll see from time to time. I think you saw it once or twice in the lecture notes up to now. So without this macro, will this work? No. So unlike MATLAB, you cannot add the constant 2 to X range, right? You have to put a dot equals, but this macro, sorry, dot plus, this macro kind of takes all the operations, all the functions, and adds a broadcasting thing to them. So certain libraries use this. The Julia machine learning library uses that. Okay. So we still have a few, okay, I think we're good to squeeze just one more thing. So a few more things from control flow. Okay, so, you know, this is just moving through, the way we created this thing is we just looked what's not in units 1, 2, and 3, and kind of augmenting a few things that you haven't seen in units 1, 2, and 3. And one of those things is, of course, there's if and else if and else and for and while. These are control flow, okay? Okay, so loops and conditionals, all right? There is a third thing called exception handling, which you will deal with in the projects. Okay, so exception handling is dealing with errors, but there are different ways of dealing with errors. For example, back in the days of Unix, I mean, Unix still exists, and the Unix functions, when you program and you do Unix system calls, the way you get an error is typically I think a -1. That's a, you know, that's like an indication of an error. So it's a return type. Okay, so often you would run the function and you check, is a return type a -1? If it's a -1, then there was an error. Okay, that's kind of check, you know, so you do a system call that creates a file. If that return -1, then that's an error. It might not be a -1, but I think it is. Okay, so that's one way. But of course, there are other mechanisms, and the two mechanisms we'll see here, the three mechanisms we'll see here are throwing exceptions, just using the error function, and assertions. And they have different purposes. So let me actually start with assertions. I don't know, has anybody used here this @assert before? It was, okay, sorry, I forgot. This is, I have a very weak memory. Okay, good. So you know @assert. So @assert 2 + 3 = 5 does nothing. But if I check if that's this, then we have an assertion error. So assertion is more a debug mechanism than an error handling mechanism. And the idea is that when you run code, you are doing defensive programming that all the time checks for all kinds of invariants that exist in your program. Okay, so I have some mental image of what's happening in memory in the data structures, and I'll assert that they happen. Okay, often you can do @assert, and then when you deploy your code to production, sometimes in Julia that's not the case, right? But in other languages, you'd write @assert, and when you have like a debug mode and you have a production mode. And when it's production mode, those asserts might not run, okay, because you've already debugged them. I mean, that's certainly the case in some real-time code or etc. Okay, so that's assertions. That's one way. So in our example here, we have, you know, we're asserting, we do a 2x2 matrix inverse, and we assert that A inverse times A squiggly equals \approx tab. You've seen that before, the identity matrix. Okay, that's like a check, right? So that's the easy mechanism. The more complicated, not rocket science, but we just need 10 more minutes for it, which we don't have today, we'll pick up next week, mechanism is throwing exceptions. So when you throw an exception, you run up the call stack and suddenly you throw an exception and that exception is thrown, but maybe down the road, somebody is going to catch it. Okay, so the whole program won't go berserk, but we're ready to say, hey, the input was bad. We'll deal with that at the start of next week. Okay, and Hoy said in Java. Yeah, so assertions in Java, right? So you're basically creating different compilation modes. I actually don't know in Julia if these can be turned off or should they be at any point. I'm sure they are. I just haven't read about it, haven't used. Any more questions before we take a 10-minute break? And so we had a whole bunch of questions about the quiz at the start. No questions at home, the 21 people at home, etc. Everybody happy? I see some nods. I'm trying to see no nods. Okay, let's take a break and Amy will set up. So we'll start in a few minutes. Okay, bye. Or one buddy at home can hear? Yep, one buddy can hear. Okay, everybody, so thanks. And let me introduce Amy. So we've got about 22 people, about 20 people at home and a good half dozen plus here. So it's a pleasure to introduce Amy Chan, and I'm really grateful for Amy to come and join us. So I'll go backwards. First of all, when we started creating this course, we consulted with a whole bunch of industry professionals, and Amy was one of them.
Was this the result of that? Okay.
Yes, that's the result of that. Yes. Oh, don't tell it to the students; they might be mad at you now. But yeah, it was. They need to do GitHub, and they need to do this, and they need to do this.
Oh, that's
yes,
okay.
yes, that's happening. So that's one.
Aren't you into something?
And Amy has a PhD from UQ in medical imaging and statistics, right? And has since graduated and is working in one of Brisbane's exciting places, Polynomial. So one of the few, it would probably be right to say math house, right?
Yeah, a little bit. We've switched a little bit. I'll talk about it, but yes, we do take mathematicians.
I'm actually interested to hear. So that's, yeah, so Polynomial is one of the big names here in Brisbane. And when she's not coding and doing statistics, you'll probably find Amy in one of the rocky cliffs and peaks around the Sunshine Coast or much farther. So thanks for joining, and let's welcome Amy for. Thank you.
Thanks, guys. Oh, I really appreciate you guys who've actually turned up in person too. I know it's not possible for everyone, but it's actually really nice to talk to people instead of talking to a screen. Not to diss you guys at home. I know you're there for a reason. Anyway, so I've been invited here to give a sort of a perspective seminar on this course that I just realized I had a bit of input into. And so I think you might find a bunch of the messages are shared. it's from my perspective as from my current job as a consultant, a mathematician, a statistician, and a software developer. So I do a lot of things at the moment. This is the classic XKCD for maths, and it's not really like this. I know you like, it's nice to think it's like this. Mathematician all the way over there going, oh, ha, ha, I'm in theoretical land. It's not like that. And it would be boring if it was like that. Also, I guess, disclaimer, I didn't really like, I have a PhD, I didn't like academia very much. So I'm not really one for theoretical maths, pure theoretical maths. So the stuff we're going to talk about today is sort of my career path so far as a mathematician, as a statistician. We're going to talk a little bit about Polymathian and how we use maths there. And then I'll do a case study of something that we've done recently. That's some statistics that I did as part of my work. And then some reflection or advice. And it's got an asterisk next to it because this advice is from my perspective as a consultant, mathematician, statistician, software developer. So take it with a grain of salt. Just because I say it doesn't mean it's true. And you get 3 perspective seminars, which is really nice. You get hopefully a few different experiences. So not all jobs are going to be like my job. Not all, if you hear my experience and you're like, oh, that sounds horrible, I don't want to do that. Not all of them are like that. This is just what I've experienced. So take it with a grain of salt. I guess worth noting my biases. I love programming. I love all this stuff that you're doing at the moment that you're learning programming. So a lot of my messaging is pro-programming. I love jobs that change a lot. I like variety, both in the maths and in the domain, and also in the skills that you get to learn. So not just the math skills, but the other skills like project management, client-facing work. So that's stuff that I really enjoy. It's not stuff that you have to do in every single job. All right, so a bit about me. The main takeaway here, I see I'm a slide behind, here we are, is that you can use the same maths in many, many different fields, and it doesn't always look like maths. So my brief career so far has spanned maths, stats, many different fields. And on the face of it, you'd say, oh, well, what did you do? Well, I did a PhD in brain MRIs. Is that maths? Does it sound like maths? What did you do at CSIRO? Oh, I was working in the agriculture team. We were flying an autonomous helicopter. Doesn't sound like maths to me. Even image analysis doesn't really sound a lot like maths. But when you get down to it, there's maths and stats everywhere, and it's just the domain that changes. So when you're looking for jobs, just keep that in mind. It doesn't have to say maths to involve maths. It doesn't have to say stats to involve stats. I also use the words maths and stats pretty interchangeably because I've switched between the two. So in undergrad, I did theoretical stuff. I did real analysis, Math 2400, complex analysis, functional analysis, that kind of stuff. It was really fun. It all ends in analysis. I thought, let's chuck in image analysis. I like programming a lot. I taught myself programming to play computer games, to write scripts for computer games when I was in uni. And a fun way to combine maths with programming is in image analysis. And I don't mean, at this point, my image analysis was not that practical. It was more theoretical. So you can frame a lot of image analysis problems as variational problems. So integrals that you're taking derivatives of, or integrals that you need to maximize a derivative of, things like that. And then once you've got an integral like that, you can do all your functional analysis. You can prove your existence or your uniqueness and stuff like that. So it was all pretty theoretical stuff and a little bit of code on the side to demonstrate that it was working. In honours, I sort of kept on with the real analysis. I switched a little bit into topology optimization. That's what Tony Roberts, Vivian Chalice used to do when they were here. And topology optimization is not topology as in mathematical topology, but topology as in structure. So if you're designing a material and you want it to maximize some properties, you want it to be really conductive and have minimal surface area or something like that, what microstructure should that have? So that's kind of, I guess it's applied maths in the optimization sense. And after I did honours, I went to CSIRO as a graduate fellow. I actually worked with the CSIRO Maths, Informatics and Statistics Division, which is really cool. It doesn't exist anymore, sadly. So that's a group of mathematicians and statisticians, and their job was to consult out to industry, but also out to other bits of CSIRO. And then they decided at some point that they didn't need that, and they would just embed all the statisticians in their domain area instead, and unsurprisingly lost a lot of statisticians. Anyway, so that job there, I wasn't a statistician there. I was doing image analysis, very practical image analysis. It was actually a lot of coding, and I'll go into a little bit on the next slide. And that was heaps of fun. The domain area was in wheat and agriculture. And then after I finished up as a graduate fellow at CSIRO, I decided I wanted to do a PhD. Went to CSIRO again. It's a fun place to do a PhD in. Different group this time. I switched from the agriculture group to the biomedical imaging group and started looking at brain MRIs. And you can do a lot of brain MRI stuff. There's a lot of maths and stats in brain MRIs, and we'll go into that too. And then after I finished my PhD, I decided I didn't like academia. It took me the whole PhD to work that out. And I thought, no, not for me. I'm going to go get a job in private sector, and I joined Polynomial. And my job there is very versatile. I've been a software developer, a consultant. I've done programming, like mathematical programming, as well as stats. So I sort of do a lot of things there. So I guess the key from all of that is that it's all maths. It's in many different fields, and it didn't look like maths.
Okay.
All right. Sorry, peeps. Let's resume. So where were we? We're talking about maths. You can do, okay, so essentially you can take your same maths to many, many fields, and don't let the lack of domain knowledge stop you from trying. So here are a few things I've done so far in my life. To the right-hand side, this is work I did at CSIRO. Down the very bottom right, you see this little helicopter. So this is in the CSIRO Autonomous Vehicles Division. They have this helicopter, it flies itself. It's the scariest thing I've seen. The safety briefing is that if it starts coming down, you run into the van because the blades are not as sharp. So it flies itself, as in you enter in a flight plan and it'll do everything on its own. You don't need to remote control it or anything. It'll take off, it'll land, it'll follow your flight plan. So what we actually did was stuff it full of cameras and sensors, infrared cameras, thermal cameras, visual cameras, and we flew it over a field of wheat, of different types of wheat, different, I don't know, varieties of fertilizers or whatever. And so that's this picture you see in the middle, which is one picture from the sky of half or a small portion of the field of wheat. So my job in this project was to take those pictures, of which there are many, 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 and they all kind of look the same because fields of wheat all look the same, and use whatever information we had, like the attitude of the helicopter when it took the photo, or its GPS coordinates, or image features, and stitch all the images together into one mega photo of your wheat field. And then you extract out all of the individual plots of wheat from there. And then on those pictures, get further metrics from that. So in the top row, you see on the left hand, this funny red-white picture. This is a near infrared picture of some sorghum, I think. And from this, you can work out the ground cover of the plants. So at the end of the day, you're extracting metrics like the ground cover of the plants. How green is it? Has it fallen over? We had a LiDAR which measures height. When wheat gets old enough, it falls over. It's called senescence. And it's interesting to know how much of the plot has fallen over at a particular time. So my job was to take these images and essentially get interesting numbers out of it. And then you'll take all of these numbers and you'll give them to a statistician on the team, which was not me. And that statistician will take all the numbers and then say, based on this analysis, this type of wheat is the best. So lots of opportunities for maths and stats in there. And I was just doing a little bit of image analysis at the start, which is, I was actually doing it in R, although I would recommend doing Python or MATLAB. MATLAB's too expensive, so CSIRO doesn't use MATLAB very often. And so to the left here is another thing I did while I was at CSIRO. It's these pictures of wheat heads. And there's this paper that my name is on. I only contributed a little bit to it. And it sounds like I know heaps about wheat. I know what vernalization and photoperiod sensitivity in wheat is. I don't know what any of that is. All my job was to take these photos of wheat. So Ursula, who's the main author, had many photos of different types of wheat with a ruler on them. And my job was just to take those photos and process them and work out what volume of wheat was visible in the photo. And this was used in a statistical analysis to say, these ones are growing bigger or faster than those ones. And so I wasn't doing stats, but I was doing maths as part of that. And then when I went to my PhD, I decided to switch. I said, well, maths is kind of fun, but stats sounds useful. So I should probably learn some stats. And so I did some stats. And this is a picture of a brain. And it's a brain MRI. And you can see in a brain MRI, you have the dark bits in the middle. You've got the squiggly gray bits around the outside. and I was working on a subfield of image segmentation or image analysis called image segmentation. And this is taking this MRI of the brain and just working out the boundaries of all the tissue types in there. So basically labeling every pixel in the image as this is where your gray matter is, this is your cerebrospinal fluid, and this is your white matter. And the idea is that once you've got a model like that of the brain, you can then work out shape statistics of bits of the brain, like how thin is your gray matter? How squiggly is your gray matter? What is the shape of your ventricles? And how do these change over time if you have Alzheimer's, for example, compared to just a normal aging process? So again, you can already see lots of different opportunities for maths and stats. I was only looking at the segmentation part, but after that, once you've got those numbers, you can derive stuff like shape statistics for the ventricles. How do I say, if I say that your ventricles are changing shape over time, what do I mean by that? How do you parameterize the shape of a ventricle? So that's maths. And then there's the stats as well, the time series kind of work. So there's lots and lots of opportunities in there, lots of different domains. It sounds like I know what I'm talking about when I'm talking about like gray matter, white matter, blah, blah, blah. I don't know what I'm talking about. Like you sound like you know what you're talking about, but really it's all maths underneath. So I guess the point I'm trying to get home is it can be very intimidating when you're looking at jobs, when you're looking at projects and you go, oh my gosh, I don't know anything about brains. I don't know anything about wheat. I don't know anything about agriculture. How am I going to function as a mathematician or a statistician here? And my message is you can. Picking up the context knowledge is not too hard. You're never going to be an expert, but you're picking up just enough to know what you're talking about, to do your maths and your stats. So I guess now I'll talk a bit about Polymathian because I work there, so I have to plug it a little bit. What do Polymathian do? You can really tell when we go from like my slides to the marketing guy's slides because he puts in way more effort than us. So this is just the spiel about Polymathian. We do industrial maths. What's industrial maths? So we're kind of cheating here. We're defining industrial maths anytime you use maths or stats in industry, we're calling that industrial maths. And we're trying to stamp the Polymathian name on that. And we'll go through some specific examples later. But what does Polymathian do with industrial maths? So we do two different things. We do software development. So we'll take a maths problem from industry, we'll solve it, and then we'll provide it back as a software to the clients. And then you sell that software to heaps of different clients. The other thing we do is consulting. So in consulting, you don't give the clients a software or a tool, you just give the clients an answer. So they tend to be more like one-off projects. So Polymathian is a maths company, although I would say more recently we've pivoted to software. So we sell maths products, but rather than solving the maths every time, why not solve it once and then sell it to heaps of people as software? So we've pivoted a bit into hiring software developers as opposed to mathematicians. So how do we do what we do? It's a mixture of things. We do optimization, and by optimization, I really just mean operations research. There's a subject here, you can learn about it. It's pretty cool. Machine learning, a little bit. Oh, machine learning, I don't know. Simulation and stats. I like simulation. I think you're going to do a bit of it. And I like stats. I like operations research. I won't comment on machine learning. So when I say we do industrial math, it's a bit like loosey-goosey, what's that? So here are some examples. So we have 6 main products that we sell, and each of them sort of solves a mathematical problem. And then you provide the tool to the client, and it just solves that problem over and over again. And they're all kind of heavy industry based. We're going to focus on Volt in a case study later. But as an example, so Solo Pilots is a product or a project that I worked on. So an example of an operations research problem is Solo Pilots. Essentially, you've got a bunch of vessels and then you've got a bunch of pilots, and you need to roster your pilots onto your vessels. So when you have ships and they come into port, the captain of the ship doesn't drive it all the way to the berth because the geometry of the port might be too weird. They don't know where the berths are that they're supposed to go. So what happens is the captain drives the ship to the harbour entrance or to some staging point. And then the port itself, like Port of Brisbane, Port of Newcastle, will put a pilot onto that ship, a Port of Brisbane pilot or a Port of Newcastle pilot onto that ship, and then that person drives it into the berth. This is so you don't get embarrassing stuff like ships bumping into berths and all that. So given your set of vessel movements of ships wanting to come in or out of the harbour, and given your roster of pilots and all these movements are tidally constrained, so they can happen at night or they could happen during the day. How do you put pilots onto those ships, respecting all the many, many rules they have to follow? So since they're doing dangerous work or high consequence work at nighttime, there are all these rules about how many nighttime movements can you do? How fatigued are you allowed to get before you're not allowed to pilot anymore? Do you actually have a license for a vessel this size? Big vessels are really hard and little vessels are easier. So it's an operations research, allocate resources or pilots to movements subject to many constraints. So you formulate that as an OR problem, you write an engine to solve it once, and then you put a nice web interface around it, and then you sell it to as many ports as you can. So that's one example of what we do. So what tools do we use to do this? So I've hacked the previous slide, this marketing slide. I'm going to write on it all the stuff that we do. So I'll caveat this. So we are a mathematics company, but we focus on software development. So a lot of this is a bit more software than you necessarily have to experience in your maths and stats life. So software development, we use Python a lot. It's very easy to learn. Basically every software engineer learns it at some point. It's a mature language, so there are many, many libraries available, and it's not as hard as C++. For the front-end stuff, because we do have a web interface, we've got all these software people who do React and JavaScript. I have no idea what they're talking about most of the time. And then for the back-end stuff, we use Amazon Web Services, which is like a nice way to do cloud computing, and a lot of Unix. So the stuff you're learning is stuff we use. Consulting, when you're doing consulting, you generally do whatever tool suits the job, and it depends on whether you're consulting in a team or consulting solo. If you're the only person doing the analysis, you use whatever language you're happy with. And if that's Julia, you use Julia. I personally use R a lot because that's what I learned going through uni, and that's what I'm fastest in. If you're working with other people, you may have constraints that you use a language that everybody knows. You may even be stuck using Excel, and it's sad, but it happens. But if you need to collaborate with a client and they only know Excel, you end up doing a lot of Excel, which is disgusting, but it happens. All right, optimization. We do operation research, that's the type of maths. We use C++ because it's fast, and we use Gurobi and Cplex, which are sort of two solvers for OR problems. I think it's got Julia bindings, I hear, and Julia is supposed to be fast. I don't know if it's as fast as C++, is it? I don't know, I'm not familiar with it. So that's where we're at the moment. Sorry? Did I teach Julia instead? I don't think I'd ever taught Julia. Oh, anyway. Machine learning, we use Python, R, and AWS. R is, I guess, again, Julia wasn't around. Python and R have a lot of machine learning modules that other people have written, which is why we use them. AWS, Amazon Web Services, is just a way they have a bunch of cloud computers essentially, and you just pay for bigger computers and put all your training jobs on them. And they have a bunch of tooling to support like parameter searching, and they have some built-in black box machine learning algorithms you can use. And then simulation and stats, Python and R, and sometimes Java as of late, but really ideally Python here. Stats, R, simulation, Python. And then all throughout we use Git, we use coding IDEs, stuff like PyCharm, stuff like VS Code. I think you guys might be using VS Code. Doesn't really matter what IDE you use, but pick one and use it well. It really boosts your productivity. So essentially what I'm trying to get through here is all this stuff that you're learning, it's useful, okay? And it doesn't matter, oh, I learned Julia, you learned R, what do I do? That doesn't matter. You use whatever you can use. When you pick up one of these languages, it is fairly easy to switch to other languages or if you're staying within sort of high level languages, because often it's just a matter of looking up what the syntax is, but you sort of know how to program already. The logic part of the coding is already done. You just have to work out the words that you type to do it. So as long as you've got one language, it doesn't really matter. So I guess what's Polymathian to me? Like what do I get to do at Polymathian? I joined Polymathian when it was really small. I was employee number 20, and we've just hired employee number almost 50, which is nuts. A small company, the benefit of that is that you can do lots of things. When we were small, we couldn't hire anyone just as a statistician because there wasn't enough stats work to sustain them. We couldn't hire anyone just as a software developer because there wasn't enough software development to sustain them. We've only just gotten big enough that maybe we might consider hiring a project manager who does nothing but project management, but even that's a bit iffy. So joining a small company gives you the benefit of trying lots of things. And that's something that I seek out and value. If you don't like that, you don't have to. So for me, I get to do stats, I get to do software development, and I get to do consulting. I get to write the proposal. I get to talk to the client to scope out the proposal. I get to write it. Lately, I've gotten to price a couple. Then you get to send it out. You get to do the work. You get to do the validation and the training with the client. And then you get to deliver the software. And then your software is online. That's pretty epic. I like that a lot. Travel's great one day. And it's a good company culture. I really enjoy it. We do a lot of things together as a company. We used to do once a year an overseas trip as a company. So on bottom right, that's us in Japan skiing. Bottom left, that's us in Tasmania, kind of overseas. Hiking in Tasmania. We have a little climb club in the middle. We have a hiking club on the right. So it's a good company culture, I guess. I don't know when the overseas trip is coming back. So there's lots of things to consider when you're looking for jobs. What do you like doing? Do you like academia? That's fine, go into academia. Do you like research? You don't quite like academia, you like research, but you want it to be a bit more practical. There's applied research. And it's not just places like CSIRO. There are R&D divisions in many big companies. Oracle, for example, has an R&D division. And I was talking to one of the ladies from there, and she's essentially a researcher. It's pretty cool. And you can go straight into private sector, many, many options. How much programming do you want to do? I don't think that you will ever get away from programming as a statistician or a mathematician. You can dial it back or you can push it up, like I've chosen to push it all the way up. You can dial it back, but you're never going to get rid of it. Just because when you're doing your stats or doing your maths, it's just going to be fastest to do it in R or Julia rather than doing it in Excel. Consider whether you want to go into a grad program or not. I don't have any opinions one way or the other. The grad program often gives you a chance to rotate through many divisions. And this can be a really nice way to try out different things without having to stick with it. So you can try it out and see what you like. So that can be really nice. Sometimes it's not just nice to go to a job. So it's up to you. Big company, small company. I've already talked a little bit about this. So often in a big company, your role is more specialized because there's enough people to take on the other roles. So you might not have to do any project management because there is a project manager. So you might be able to find a job that's more like just stats, just maths. Small companies, you tend to have to do more than one thing. And some people like that, some people don't. Do you want to work in a big team or as an individual? I actually do both of these in my job. So when I'm consulting or working as a statistician, I'm generally working on my own. So there will be multiple people in the project, but I'll be in charge of the stats. But when I'm writing code, we're writing in a big team. Like you're using Git and heaps of people have touched the code since you just pulled it and you have to merge it and it's a pain. So it can be different. Individual can be nice because you get more control, but team can be really nice because it's so good to have other people to talk to help, make suggestions and do things. And then company culture, very important to consider. You're at work for a third of your life, 8 hours a day. Be happy there. Don't get stuck in a job that you don't want to do. Vacation scholarships. I've done a bunch of vacation scholarships at CSIRO. I highly recommend vacation scholarships. Not necessarily CSIRO. CSIRO is great. They pay the most, but anywhere really. They're, again, just really good ways to get a little bit of research for vacation scholarships, internships, get a little bit of experience, just decide whether you like it or not. They're really low risk. Maybe you do a vacation scholarship at a uni and you go, oh my gosh, I hate research, or I hate that area of maths. I thought I loved it. That's a really low risk way to try them out. So I really recommend these, whether they pay or not. They also look pretty good on your resume. All right, so let's do a case study. A case study is loosely termed. Statistics is not just statistics. And it's kind of expectations versus reality, I guess. This little XKCD, this person says, how do you get graphs from a Polaroid photo into Excel? Funnily enough, in one of our projects, we had screenshots of a graph from a software and we're asked to get the equation of the graph from the software in the screenshot because they couldn't find the data that was making the graph, even though they knew they had it. So this is actually happens. All right, so we're going to look at a product called Volt. Volt is an energy product. Let's pull it up. Actually, here's one I prepared earlier. Okay, so what does Volt do? Volt, marketing slide, helps energy and utility operators optimize asset dispatch network operations that their portfolios. This is all like management speak. I have no idea what that means. What does that mean? So I'm like a power steam person. I have a bunch of different assets. I have a hydro dam, 2 of them. I've got 3 wind farms. I've got 3 gas turbines. They take gas and make power. I've got a cogeneration plant. This is something that makes both power and steam. I've got a boiler. It takes in rubbish and you burn the rubbish and make steam, money. I've got a steam turbine. You put in gas and you make steam. So I can make steam and I can make power. And on my site, I have a bunch of factories and they say, well, I need this much power and this much steam. I need that much power and that much steam. Separately, there's an energy market. You might want to sell power into the grid or buy power off the grid. So the question is, given your supply at the moment, so given like how much wind your hydro and wind can make, which you can't often control, given how much gas you have available or how much it costs, given what all your customers want and your market conditions, how do I fulfill this demand? Just say my customers want 10 tons of steam here and 100 tons of steam there and 100 megawatts of power. What is the cheapest way for me to supply this? So this is the problem that Volt solves. It's a network flow problem. It's operations research. We actually have this running live. Let's see if this works. We actually have this running live at a site. And they use it to dispatch their assets. So they go, oh, they look at it and it tells them how to operate their assets. This is quite funny. So it shows them the difference between the optimal margin and their actual gross margin. So it maximizes gross margin. And at the moment, there's an error with one of the data feeds. So the actuals is way above the optimal, which is not usually what you want to see as a mathematician. You say, oh, we have the optimal solution. Oh, your actual solution is beating it. But this is actually because one of their tags failed down here. But anyway, so this gets used in real life. So minute by minute, people use it to dispatch power stations. So that's pretty cool when you see stuff that goes into real life like that. So that's Volt. That's what it does. So what it, where's my piece? Where's my slides? So what it does is that you put in your demand, you put in your supply, and then you click solve, and then it gives you a bunch of results. And the results that it gives you are what to generate from each asset at each time period throughout the day to make the most money, because you always want to make the most money. So this one says that you should make 140 megawatts from these wind farms, 130 from that one, blah, 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 blah. So that's what Volt does. So in terms of maths, what is it? It's mixed integer linear programming. I suppose I should, present these slides. So it's mixed integer linear programming. It's a network flow. So when you do an OR subject, you'll probably do a network flow problem. It's that, but fancier. Very broadly, what you want to do is maximize some objective function subject to a bunch of constraints. And the objective function for Volt is, plus or minus a bit, you want to minimize imbalances in flow along the network. So you want to have your network flowing. Energy in has to equal energy out. The sum of all the energy you generate has to equal the sum of the energy you pull. You can't have magical steam and energy just disappearing off the network somewhere. Usually when you do OR, when you do it in your course, you'll implement these as constraints rather than as your objective function. But we have implemented it in the objective function because sometimes you get tiny mismatches in flow because of rounding errors. So it turns out there's a sensor on that piece of equipment that records energy out. And there's a sensor on that piece of equipment that records energy in, and they mismatch by a tiny bit because they're physical sensors. And if you have a constraint that says energy in equals energy out, you'll get an infeasible problem. So we have it in the objective function, say minimize the number of imbalances on your network. And then the second objective is maximize gross margin, which is the one everyone cares about. So the constraints that you operate along. Asset constraints, so your plant could be down for maintenance, you can't use it. Limits, stuff like this steam turbine can only make at most 10 tons an hour of steam. Or you can't turn on that cogen plant unless you're making at least 20 megawatts of power, stuff like that. You get time-based constraints, so this is constraints that happen over multiple time periods. So if you want to start up the cogen plant, it's going to take 3 hours, and it ramps up following this profile. And then you have daily quotas. Maybe you've got a bucket of fuel for the day. You've got a gas contract that says, I need to pay for at least this much fuel every day. Or you have some sort of total amount of power you need to generate in your contracts. And these are the kind of constraints that are in the problem. And then the output, as I showed you, is just how much steam and power to generate every time period and how much money you made. So the 3 main inputs to Vault, besides the day-to-day stuff that changes, stuff like power prices or whether something's under maintenance, there's the network model, first of all. So the network model is purely this graph. How does everything connect to everything? How do your pipes connect? Turns out this cogen can feed steam into this, can feed steam into the steam plant, which can make more power, the steam turbine. We have a financial model. This is arguably one of the very important parts. If you don't have a financial model, how do you know how much money you're making? This is stuff like how much you're paying for fuel, how much you're getting for energy, how much does it cost you to run your asset? And then finally need an asset model. And this is what I'm going to focus on today. So if I have a steam turbine, or here's my energy from waste boiler, you throw in rubbish and it makes steam. If I throw in 10 tons of rubbish, how many tons of steam do you get out? That's an asset model. So the case study that I'm going to go through is, what is the asset model for a cogeneration plant? Cogeneration plant, remember, it makes power and it makes steam. And to complicate things, you can make more than one type of steam. You can make high pressure, medium pressure, low pressure steam. And so the client says, well, the client says, configure Vault for us, please. And we said, great. So if you needed to make 10 megawatts of power and 10 tons an hour of steam, how much fuel would that cost? And they're like, you know the answer, right? This is your cogen plant. Maybe this much. Like, well, what's the equation? Like, they didn't know. So, job for a statistician. They have a lot of historical data, and we have to derive the asset model because they didn't know it. I think nowadays, when you buy one of these expensive plants, I feel like in the manual somewhere or in the advertising would be some sort of estimate of how much fuel you would have to pay to produce a certain amount of output. But this, the manual they sent us was 500 pages long and didn't have any of that stuff in it, sadly. All right, so step 1, I'm a statistician, yay. So send us, please, a spreadsheet which has gas in, power out, HP steam out, MP steam out, LP steam out, and anything else that might be relevant, stuff like temperature, humidity, I don't know, you tell us, you're the expert. What do we get? What's wrong, slides? This is what we get. Right, this is what we get, a spreadsheet. It's got many, many, many columns of stuff. None of the columns have human readable names on them. It is in long format. That's a win. So it's got like time stamps in the rows and then columns across, which is nice because often you get data that's not in that format. So step 1 is not exploratory data analysis. Step 1 is get the data. This takes a lot longer than you think. Lesson 1, getting the data takes time and good communication. So we send them this request, give us gas, power, steam, HP steam, MP steam, LP steam. And that's kind of easy. Like if you looked at your cogen as a black box, just send us what goes in and what comes out, please. Anyway, so we sent that request to them and they said, oh, well, the cogen plant is not a black box. It has 2 gas turbines that burn fuel and make steam, and then it has 1 steam turbine. You send the steam from the gas turbines into the steam turbine, it makes power. You can pull out some of that steam and sell it as steam if you like. When you put high pressure steam into a turbine, you get power out and you get slightly lower pressure steam out, like medium pressure steam. So that steam you can sell as medium pressure steam, or you could put it back into the turbine, get a little bit more power. And then the steam that comes out of that is low pressure steam. And that steam you can sell as low pressure steam, or you can send it back to the top part of the gas turbine and reheat it, and then feed it back into the steam turbine. And all this confusing stuff. So we got all these diagrams from the engineers and they said, okay, which steams did you want again? We don't know what you mean. And there's a bajillion different steam inputs and outputs. And so you need to communicate well. And it took ages because it was partly because we didn't know the context, and it's partly because they knew too much context because they know precisely how a cogen plant works. We don't know at all how a cogen plant works. And it took actually a while to communicate that we want to consider the entire cogen with all the little gas turbines and steam turbines in it as a black box, and we just want to know the overall ins and the overall outs. And that took a lot of time. So I guess that's lesson one. You need to communicate a lot. It's a big back and forth process. Okay, so we get the data, it's great. We know what everything is. We've got a column that's labeled steam, a column that's labeled gas, so we can start doing the analysis. But the data is never how you like it. You're going to do a lot of data mangling if you're a statistician. So here are some examples. So top left here. Here are the columns we were looking for, IP steam and HP steam. That's great. They're the two bits of steam we were after. So we do the analysis, and then the engineer comes back and goes, oh, that's not IP steam, that's HP steam, it's just mislabeled. Oh, that thing that says HP steam, that's just water. Ha ha ha. That's just what happens. You might ask for data in long format. So that's on the right-hand side here. So long formats where you have, for example, time down the x-axis or down the rows, and then you've got the value down the columns. And they instead give us a format that's like time out wide, and it's an Excel sheet. They've got little colored boxes to indicate their data, and the color of the box holds information. And you have to get that into a computer because they just sent us 5 of those, and I don't want to type them in manually. So you end up writing a script that reads this stuff in. The reason that you often get data in wide format is that it's really human readable. This is a maintenance schedule. It's very easy to see. Long format's hard to see, but long format's easy to process. So you do this kind of manipulation all the time. So bottom left, here is some data of fuel versus time. And a bunch of it's rubbish, but you don't necessarily know it's rubbish. So there's a bunch of zeros down the bottom there in blue. That's when the sensor was out. That's kind of easy to spot. You've got these weird like vertical spikes happening in the green. And it turned out we didn't know what this was. You can't just say, I don't like that data, chop it out. You have to work out why you want to chop it out. So we emailed them and said, well, what's happening here? And they said, oh, we were doing testing that day. The ascent went down, like the gas turbine tripped. And then we had to do all this weird stuff to start it up. So now we know, we said, well, give us all the other dates that this happened. And then you can cross out all the data in green. So you're always going to get dirty data like that. Bottom middle. So this is a bit of sensor data. They said this tag is 0. We did a performance test. We set this particular input to 0 and we changed the rest. And it wasn't 0 at all. And it turned out the sensor was just rubbish. And then this is some truncated data to the right. So on the right here is a steam profile in the black line and the fuel profile in the pink and the blue. And the pink and the blue are 2 different fuel sensors. And the blue always stopped at like 4,000. And it turns out there are 2 fuel sensors, and one of them is a high range and a low range. One stops at 4,000, one starts at 4,000. Didn't know that. They didn't know that either. So they went looking and they said, the high range sensor's broken. Sorry. So that's what happens. So this is also a back and forth process. Communication is really important, and graphs are really important. So whatever you use in Julia to do data visualization, really important. You can try and explain to the engineer in words, at this timestamp, the data looks like it's always at 2,000 or 4,000 and it's not doing anything. Or you can send them this picture and say, you can see that the gas is meant to be going up, but it's stuck at 4,000. Anyway, ages later, you get beautiful data and you get to do some stats. And this is the fun part. At the end of the day, this particular stats was a linear regression, a multiple linear regression. So it's fuel versus power plus all the 3 types of steam plus an intercept. There's a little bit of an interestingness in it, in that there's 2 ways to operate this cogen. You can operate it in normal mode, and you can operate in like super turbo mode, which is called duct firing. And that's when you feed in a bunch of extra gas to get a boost in performance. It's not as efficient, it's expensive. But it's a way to increase your output when you need it. So the method itself is just a regression, and the cool part with the breakpoint. So there's a breakpoint between the pink and the blue. It's hard to see, but there's a little kink in that straight line, and the breakpoint itself is estimated as part of the regression. So you look at this and you go, if I gave you this data, you could come up with this model. You absolutely could. The stats itself wasn't hard. And I find in consulting, and I'm sure it's different in other jobs, and in consulting, the stats itself is often pretty easy. So people say, oh, you're a statistician, you do really cool stuff. And you say, oh, I did a linear regression, yay. That's how it goes. But the flip side to that is don't let perfect get in the way of good. I mean, of course you can improve this model. We didn't include ambient temperature, humidity, stuff like that. They had very small effects. They were actually not significant. But don't let perfect get in the way of good. A lot of people who come out of academia, me included, because I came out of a PhD, you're like, oh, we can look up the latest cutting edge, theory on how to apply to this problem, rah, rah, rah. But you know what? The linear regression does the job. It answers the question and it does it quickly, and that'll do. So just be wary of that, especially if you're coming out of a research or really high academic background. And then you think your job's done because you've just done your stats, you've got your answer. But communicating the results is even more important than the stats itself. So I didn't mention anything about p-values, confidence intervals, assumptions checking. I did do it all, but this is not what you communicate to the client. Do you know what a confidence interval is? Do you remember the words that you memorize that you write on the test, because you don't actually know what it is, but you're like, oh, I'm 95% confident that the parameter is somewhere between this and this. What does that mean? You don't know what it means. Does the client know what it means? No, doesn't matter to the client. So you do your due diligence as a statistician, but you don't expose all the details to the client because it's just not useful. The asterisk is there because it depends on the client. Sometimes your client is the data science team of another company. That's a blessing. They know what you're talking about. You can talk to them. That's fine. Sometimes your client is the operator of a cogeneration plant. They don't know any statistics. They don't care about that stuff. And if you talk about that stuff, it confuses them. Stuff like, how do you visualize fuel versus 4 other variables? This is like a hypersurface or hypercube, right? What we ended up doing was projecting all the outputs onto one variable, which is what you see in this graph here, and then putting the variable they cared about, fuel, on the y-axis. So essentially, work out what level of detail is appropriate to the presentation. This is not necessarily your client, to whoever you're presenting to, and only expose them to that level of detail. And sometimes you do some really cool stats and you're like, oh, I fit this autoregressive ARIMA model with this, this, and that. If that's lost on the client, sadly, you know you did these cool stats, but you're just going to have to present them the results instead. And at the end of the day, confidence intervals, too hard to explain. What they actually cared about was, we just made up this is not a mean squared error or anything. We've got this statement, 95% of your data points are between minus 1.6% and 1.8% of your actuals. Essentially, your data, if we plot all of your data along this line, that error bar of 95% of your data points is minus 1.6% to plus 1.8%. So this model is accurate to plus or minus 2% on your actuals when we go against your actuals. And this is a lot easier to explain than a prediction interval, and it makes sense to them. Like, oh, plus or minus 2%, that's okay. Because it turns out their sensors were only accurate to within plus or minus, I think, 3%. So that's good enough. And a good statistician or mathematician is going to try and reduce the language barrier. If you notice there's language that your clients always use, you try and use that language too. If there are charts and metrics and KPIs that they use a lot, try and frame your results in the same charts, metrics, and KPIs, even if they don't necessarily make sense to you. This just reduces the language barrier when you're trying to communicate your messages. So a couple of things here. So originally this slide, this is how we presented it to the client. It had the words linear regression on it. We did a linear regression. It had the equation on it. But this was really confusing to a bunch of the engineers, because when you see a linear regression, you look at the gradient's constant, right? So it's the power per fuel or whatever, or the fuel per power. And one of the key metrics that engineers use on a cogeneration plant is the heat rate, and it's the fuel per kilowatt hour. And this is non-linear. So as you increase the amount of power generated, your heat rate should go down. And so this was really confusing to the engineers, because they see a linear equation and they go, hang on, heat rate's the gradient of that equation and it's non-linear. And it turns out that heat rate, when they calculate it, includes the intercept. And so when you're dividing through an intercept, it's not the pure gradient, right? It's your mx plus c divided by. And so because of this language we were using, linear regression, it's what it is. It didn't conflict with their idea of the heat rate, but it was confusing them. So we just took that language off, and it made a big difference. It's a silly thing, but it makes a big difference. Down the bottom of the graph, I've put output is some combination of power and steam. We call this load, like how much load is the plant under. Turns out that load has a special meaning to cogen engineers. It means something else. It is also a combination of power, HV, MV, and LB steam, but with different coefficients. So if we're using the word load there, it's instantly confusing to them. So we just changed it to output. So these are things that I mean, and they seem small, but they make a big difference when you're communicating your results. If you're communicating your results and your clients are coming with the same questions every time, think about how you can change how you communicate. All right, lesson learned. Don't let perfect get in the way of good. We've already discussed that. Version control, very important. Here's a little snapshot of a small number of the R scripts that we wrote to do this work, or that I wrote to do this work. Version control is so, so, so important. So I know like you hate Git, but you got to learn it. Visualization, very important, because a graph says 1,000 words. And communication, you're never going to get away from communication as much as you like. Even if you're a mathematician in a team of mathematicians, you're still going to communicate your results to someone. And that someone at one point is going to be a non-mathematician. So I guess the summary of this case study is statistics is not just statistics. So it's not just this little cool bit in the middle. Statistics actually includes all the stuff before, getting your data, cleaning it, talking to the client. It includes all the stuff after presenting your results. That's part of statistics. Sad message maybe, but that's true. And again, you can dial this back a little bit if you want. If you're working in a huge team of mathematicians somehow, I don't know where they exist, maybe you don't have to do quite so much communication to non-mathematicians. Maybe you work in some magical wonderland where your data arrives in a magical, amazing, labeled, beautiful format. It's not going to happen, essentially. All right, so I'm aware we're running a little bit over time because we had that little bit of delay. So we'll go a little bit fast. This is the last bit. So some tips from my experience so far. You have numeric literacy and you have programming skills. These give you many, many career options. The jobs aren't always called mathematician. They can be called analyst, data analyst, modeler. They might not even be called that. Many big companies these days have a data science division. BHP does, Boeing does, Qantas does, Virgin does. Who are the others? Anglo does. Rio Tinto, they do some really hardcore stats in their little maths division. So there's often a little, if it's a big company, they often have a little maths stats division that consults out to other parts of the company. It can be hard to find those jobs, but they're there. Sometimes you just got to ask. If you've got maths and programming together, as opposed to just one or just the other, you have a lot of freedom to move sideways. And so sideways, I mean, like I started as a statistician, I guess, and I'm sort of doing a bit of software development, and then I'm going to go into consulting, and I can keep pivoting as much as I like because you've got those key skills. And it's not necessarily the specific maths you learned. I learned real analysis like epsilon delta proofs. Have I ever done an epsilon delta proof ever again since Math 2400? No. But it's the skills you learn. So it's the problem solving, it's the critical thinking, the thinking skills that I learned in subjects like 1061 and 2400, how to write a proof and think really logically and precisely, being precise in your language. These are things that you learn when you're writing proofs. And it's really valuable. And you can see when we get people through maths degrees and we get people through non-maths degrees, and their language is very different. The way they think about problems is different. So these are the skills you want to highlight. A lot of companies are they kind of know this already, but these are skills that you can teach them in your interview. Just say, I have these skills, even though this maths is not my kind of maths, you know? You got to learn to program. I'm a bit biased. Yes, I do a lot of software development. You have to learn to program regardless. There's two types of programming. There's scripting and there's software developing. So like scripting is kind of what you're doing now. You're writing a script or some code to do what you need to do. It's generally one file. It might be a few files. It's not generally designed for other people to come back and look at after. If one of my colleagues has to come back and look at all the scripts that I wrote for that stats job, the case study, like good luck to them. I can barely go back and understand what I've done, but it's all there. Software developing is very different. This is when you're in a big code base and you're thinking about the architecture of your code to make sure that other people can come and maintain it, to make sure that other people can extend it. It's very, very different. If you're going that way, learn about object-oriented programming, learn something like Python or C++, and learn different coding patterns, coding architecture patterns. So if you want to go that way, software development as opposed to scripting, and I'll be very clear, as a mathematician, you don't have to do software development. That's just something that I chose because I enjoy it. Scripting is fine for your job as a mathematician, statistician. If you want the option to take a software developer job, you will need to learn this stuff. It can be a bit hard applying for a job if you don't have that on your resume, software development. because there is a difference between the two skills, and saying I learned to program in my maths degree is kind of a red flag, because you're like, we know there's a difference between the two. And if you think you can do software development from your maths degree, you're wrong. So if you're going that way and you don't have a software degree, it's not the end of the day. I managed to do it. You just got to be doing it in your own time. Have your GitHub account, have your little toy projects, upload them there regularly. A good way to start if you've got a code base, a lot of cool tools these days are open source and their code base is on GitHub. And if you find a bug in it or you want to make an improvement, you can do a little pull request, pull the repo down, make your little change, submit it back. This can be a really good way to get into it. So they're different things. Ask me about them later. You can pivot between the two. For most mathematicians, statisticians, scripting is enough. Yep. Your grades. This is interesting. They matter and they don't. What do I mean? We will give an interview to anyone who has straight sevens, because someone who has straight sevens is smart, right? That doesn't mean that you're going to get the job. We've interviewed people with straight sevens and they're just not suitable for the job. So the grades can get your foot in the door. They are important for that. Once you go to your interview, so the grades matter at most for your first job, because you've just gotten like 10 applications and you need to pick some of them, and you have no idea whether they're any good at programming, but they got like a 7 in their programming degree. So you go for that. So they matter for your first job. The moment you've got any sort of relevant experience, they don't matter at all. They'll get you into the door for your interviews. So I would say focus on them, but don't like cry if you didn't get a straight 7 or whatever. So they're good to have, but they're not absolutely necessary. Right, learn version control. Every single job I've had has version control in it or has used version control. In some jobs like software development, it's more important than others. Using Git on your own, which is usually what mathematicians and statisticians do because they're the only ones in the repository, is very different to using it in a team. That's not necessarily a good or bad thing, just know that they're different. If you're working in a team, you'll have to learn way more Git than you will have to learn here. A funny thing on this XKCD is that I find that binary files like PowerPoints, Word docs and stuff, don't version control them because it doesn't make sense to merge a document, somebody's docx with your docx. You'll get a malformed document. Sadly, we revert to this version 1, version 2 kind of business. And be ready to learn. So you're never going to get to your job and have all the skills required for it. You're going to start, you start a new consulting job and someone says, work out the asset model for my cogeneration plant. You go, oh, great, what's a cogeneration plant? You're never going to know it all. Be open to that. That's okay. It doesn't mean that you're somehow not good. You have to be capable of self-learning. So you'll be able to learn to help yourself. Stack Overflow is your best friend here, but also ask for help often. And this is important, especially people who come from research backgrounds. They're used to doing it all themselves because your PhD has got to be your own work, right? Ask for help all the time. You've got people all around you who know what they're doing. Ask for help. So as an example, my latest project, I've had to learn Java. I've had to learn Excel, way more Excel than I ever wanted to learn, like macros. It was horrendous. And I've done a machine learning certification using Amazon Web Services. So you're always going to be learning in a job. Just be ready to learn. And finally, soft skills can't be ignored. You cannot ignore them. You can vary how much client work you have to do. I do a lot because I like it, but you're still always going to be doing some. At the start, you always have to ask questions of someone because you're never going to arrive at your job as an expert. At the end of your project, you're always going to have to explain your work to someone. So the key is finding the appropriate level of detail. If you're a painful introvert, I used to be a painful introvert. I still am an introvert, but not painfully so. Fake it till you make it. It works, right? It's horrible, but you just fake it till you make it. But I'm confident, yeah, give the talk. Pretend you know what you're talking about. And you feel like a fraud because you're pretending like you know what you're talking about. After a while, you realize you know what you're talking about. So just give it a go. Fake it till you make it. Right, bear with me for a moment. Last, other tools worth checking out. So these are some tools I mentioned or maybe didn't mention in my talk. I'm not going to go through them all. This is just sort of a list if you want to look at it later. Pandoc compiles any format to any other format. This is really useful for assignments. In particular, it compiles Markdown to PDF, Word, HTML, or PowerPoint. The Markdown to Word has actually been quite useful for me. In the background, I think this is what Jupyter is using. The R version of Jupyter is called R Markdown, and this uses Pandoc in the background. And really all your Jupyter notebook is doing, all the R Markdown is doing, is it evaluates your R code and generates a Markdown file, takes the Markdown file, and then compiles it to whatever you need. If you use R, learn ggplot. I'm sure there's an analog. There's a copy of it in every other language now. It's a very steep learning curve, but it's a tool that I use really all the time. Commander, if you're stuck in Windows, there's a tool called CMDER. This is what it is. It's like a console, but you know, command prompt in Windows doesn't understand Linux commands like ls and stuff like that. So Commander is like a really thin shell on Windows that offers you some Linux commands. You've got grep, you've got find, you've got ls, you've got all that kind of stuff. So if you're Linuxy, but you're stuck on Windows. And the last thing you can do is actually install Linux on Windows. So this is Windows subshell for Linux. This is Ubuntu running in Linux. So there are ways to get Linux on Windows if you want. And then despite liking code and Jupyter and being on your high horse, sometimes you are stuck with Excel. And sometimes you're stuck with PowerPoint, and sometimes you are stuck with Word. And the reason is, if you want to send, you might have this really cool R Markdown script like in here, and it makes this awesome PowerPoint that you're copying or you're using for your presentation. This is all generated in R Markdown, which is like your Jupyter notebook. At some point, someone's going to want to collaborate with you on that, and they're going to add comments and pictures on the slide. They're going to add content. I don't want to back merge them into my R Markdown. So in situations like this, you're better off staying in Word or PowerPoint to begin with. The compromise I make is that I have this generated presentation and I copy paste these tables into the actual presentation that all my collaborators are touching. All right, final thoughts. Don't be depressed if this talk made you feel depressed. And go, oh my gosh, I don't want to do all that client work. I don't want to deal with all that stuff. Don't be. This is my perspective. This job is not the same as many other jobs. We've just hired someone who came from Boeing. She did pen and paper maths. Pen and paper maths, imagine that. Proof of concept stuff, and then would pass it off onto a team of software developers, and the software developers would implement it. So there are jobs that are more mathsy and more statsy if you want. She still had to talk to software developers, so the communication is still part of it. And then lastly, it's never too late to pick up new skills. Just say you get, you graduate, oh my God, I should have learned software development. I'm unemployable. It's not the case. You can always pick up new skills. Alrighty, I'm sorry for going over time. That's all I have to say. Thanks for listening, guys.
Thank you, Amy. Sure, there are claps from the people at home. Maybe you want to turn on your camera if it's off, so we can stop sharing. So I think it was really worth to stay the overtime and the glitch. Is there a question or two from here or from home? Yes, Paul.
I was writing scripts for a MUD, a multi-user dungeon. It was a text-based one. It was called Dark Legacy. It doesn't exist anymore. It's like World of Warcraft, but it was much, much older. It was entirely text-based. You had to type stuff like cast magic missile. You had to type that in. I type really fast. You can use regular expressions and Lua to capture text from the game and then respond to it. So like something attacks you and then you cast magic missile at it, stuff like that.
Is there any other thought or question? So it is late, but oh, yes.
Internships or grades? Both internships. That's for the experience. That's helpful for you too, because you might discover some office environments you don't like or types of work you don't like. Yep. Finding the projects, yeah, so a lot of people advertise. It might be a bit late. No, it's not too late. So a lot of the big companies just look up vacation scholarships. They've got them. A lot of the universities offer them too. Saro offer them. I don't know. Sometimes you can email companies, say, hey, do you offer an internship? Often they don't. But usually if they offer one, it'll be called like vacation scholarship or something like that. It'll be on their website. Big companies, generally, big companies. Okay, but you'll have my email, okay? So email me if you've got questions.
And just one last one in the chat.
Oh, yeah. Are we offering any internships? Oh, are we offering internships at Polymathian? So this is a little odd. We actually don't offer internships. No, sometimes we offer internships at Polymathian, ask and see, essentially. We generally prefer casuals. So we hire casuals. It's a bit rough because you've got to be there at least 2 or 3 days a week full time. That can be rough. And I would say your grades always trump a casual job, like your uni work is more important. We're hiring software developers at the moment. Software developers with maths is amazing, but mainly software developers. I know that might be a bit sad to hear in a maths and stats lecture. So as I explained, we sort of pivoted a bit in Polymath. We do maths problems, but we deliver software.
Well, thanks a lot. I must say this was such a useful presentation with all the tips. So thanks again, Amy, and it's worthwhile. Thank you.
All right. Email me, all right? You've got my email somewhere, I'm sure.